with you again this morning doing our week 9 session on the normal distribution. And I just wanted to refer briefly today, we'll spend a fair bit of time with these tables. These tables can be found on page 784 of your textbook. And excuse me, what I'm thinking is that if you were doing an exam, it's sometimes when you're reading some of this data off here, I do recommend having perhaps the paper version in your textbook available, and with a ruler, you can use your ruler to just make sure that you pick up the right figures. It could save you some marks. So got that out of the way. That's my little announcement for today. Let's launch in. Possibly 40 to 50 minutes to walk through some slides on the normal distribution. There are plenty of practical examples to work through today, and so just stay with us, take a break if you need to at some point, but the idea again is that you would be looking through this at your own pace before our class on Monday. So what's this normal distribution all about? If we were to graph, for example, the heights of people in the population, and so here's 0, and here's the x-axis, people getting taller and taller, we would find that we'd have a few shorter people down this end, closer to the the 0 mark, and then climbing up, still shortish, getting to the average right in the middle. Remember from 2 weeks ago, methods of central tendency, we had the mean, the mode, and the median right in the middle. So that's what's happening here. We've got the mode, the highest score, the mean, and the median right in the middle. So the average height. So more people would be gathered around this height, and then there'd be fewer as we get taller and taller, and just a few up in this area in the very tall range. So it's what can we notice about this distribution? They talk about it being a smooth bell-shaped curve. We can see just in this particular distribution here that it's basically mirror-shaped. That half the distribution is a reflection of the other half, if you like. And so what happens is all of the data is gathered, 100% of the data is under the whole curve, but our tables, when we start to look at them today, they only go to 0.5. The theory being that, well, look, it's a mirror image of the lower half is a mirror image of the upper half, and therefore if we can work out the areas below the mean, we can also work out the areas above the mean with the same set of tables. Save some ink, save some space, does the job. So these are the sorts of data that we might be recording that might follow a normal distribution: heights, blood pressure results, IQs, lengths, so often weights, battery life, exam scores. Let's think battery life. You'll have a few batteries, so you'll have the average in the middle, and then you'll have a few that will last longer and a few that don't quite last that long. So, okay. Here's another representation of the normal bell-shaped curve, if you like, with the mean, the population mean. Whenever you see mu, you know it's the population mean right in the middle. And this particular distribution here, they've all got the same mean, but the scores are clustered closer to the mean. So there's less variation in this set than this flatter curve, this one with the flat kurtosis. Wide range of scores. Mean still in the middle, mode and median in the middle, but a larger standard deviation. Here we've got the same standard deviation, but 3 different population means. Well, what they've discovered is they've looked at the relationship between the mean and the standard deviation. They've found that no matter what shape the distribution is, whether it's a flat curve or a steep curve, that 68% of the population would be within 1 standard deviation above and below the mean. So yeah, 68 above and below. They would lie within 1 standard deviation, 34% above the mean and 34% below the mean. About 95% of the data would be within 2 standard deviations of the mean, and we're going to discover later on why Again, they've discovered in their distributions the area under the curve that within 3 standard deviations, about 99.7% of the data would be there. So we've said before that the total area under the curve is 1. Of course, half the curve is 0.5. So let's put it together in some examples, see what we can do. We've looked at 200 males, 200 females, we've selected a study and we've recorded their heights. We've found that males have an average height of 178.6 centimetres with a standard deviation of 7, and females a mean of 164.5 with a standard deviation of 7.7 centimetres. So we'll put that together, and in a distribution, we can, just by looking at it, you can sort of see this bell-shaped thing happening. So we've got a low frequencies down this end near the 0, and then they're clustering, gathered around the average, and then shaping off to the higher heights. Female, same sort of distribution with our data. So we've got that bell-shaped curve happening. And so that's what it looks like. If you were to graph it, we can see from about 2 weeks ago, we've got the histogram and then the polygon joining up the central bars of the histogram. And so we can see it's starting to look like a bell, both curves looking a little like a bell-shaped uniform distribution curve. So let's put some more data together. We're going to piece together how do we go about solving the area under the curve. We can, if we know the mean and the standard deviation, then we can work out a whole lot of probabilities, and that's what today is all about. So we're going to crunch some formulas, we're going to look at some areas, and by the end of this session, hopefully you've got a pretty good idea of how to attack the questions. The thing I like about these questions is there's just a few little tricks, and once you've got these tricks, there's only so many ways that the data can be represented so that you can, I call them bread and butter questions. They should be easy marks for you once you get into the routine of solving them. Just work with good accuracy, good clerical accuracy to pick up the right figures, crunch the numbers in the formulas, and you should get, it's possible to reasonably easily get full marks in a question like the normal distribution in an exam. So these guys have found the mean was 10 hours with a standard deviation of 2. And it says sketch a normal curve. This is always a good idea. I always recommend having a piece of paper handy that you can just quickly whip up a bell-shaped curve. If we're in the class, I draw one, for every single question, I draw a bell-shaped curve so we can picture what we're trying to find. And this says I'd like you to find the proportion of days where the repair time was between 8 and 12. So we would draw ourselves a graph and always put the mean right in the middle. There it is, mean hours of 10. And we're trying to find this area between 8 and 12. This time, and so what's interesting, we're going to, in a moment or two, we're actually going to find the area. The tables will give us the area back to the mean. They're always designed to give us, we look up a z-score. We're going to find a z-score in a minute, and we're going to look up an area and it'll show me the area back to the mean. So here we want to we'll have to do the calculation twice. We need to do it here to find this area and here to find this area, and then add the two together. For B, it says more than 11 hours. 11, by drawing the graph, we can see that 11 is above the mean of 10. And we're trying to find this area up here. Remember, the tables in a minute or two are going to give us, when we do a little formula, we can look up the area, this area. The tables will give us this area. And so for us to find this area here, we know that the whole graph is 1. Half the graph is 0.5. So if we, for example, knew the tables were telling us that this area was 0.2, then this area must be 0.5 minus 0.2, and that'll give me 0.3. 0.3 plus 0.2 adds to 0.5, half the graph. C says less than 9 hours. Again, by drawing the graph, we know the mean is in the middle. We know what area we're trying to find. It's below. Same sort of deal as this question here. The tables can give us this area. We'll need to, once we find that area, we'll need to go 0.5 minus that area will give me this area. Last one, D, between 11 and 14 hours. Again, we need to do, there's two calculations there, two formulas to calculate. We'll need to find the area, and the tables will give me the area all the way back to the mean for 14. Then we'll find the areas from 11 to 10, in fact we've found it up there in B, and what we'll need to do is find the total area minus the area from 11 to 10 will give us the shaded part. So they're the techniques for solving the normal distribution. Let's go further and see what we can find. So the first thing, we've got this little Z formula. Z score really is just showing us how many standard deviations are we away from the mean. So we pick up a particular piece of data. In the formula you'll see in a minute, it's known as X piece of data, the unknown piece of data, minus our population mean over our population standard deviation. Let's have a look at the formula. So there it is there, the piece of data we're looking for, the boundary if you like, minus the population mean over the standard deviation for the population. So get used to seeing those symbols. That sigma always represents the population standard deviation. Mu, that Greek symbol, always represents the population mean. So here's the full-blown question, if you like. It says, suppose the weights of certain elephants are normally distributed with a mean of 20 tonnes and a standard deviation of 2 tonnes as the weights, and mice, a mean of 30 grams and standard deviation of 3. So we've got to try and work out what's the probability that an elephant has a weight between those range of tonnage and a mouse between those weights in grams. Okay, so we're going to draw two graphs to represent that. First graph, put the elephant mean in the middle, 20 tonnes, and the question says, hey, what's the probability that it weighs between 22 and 20? So that's handy, it just 20 is the mean, so we've just got to find that area back to there. And the mouse, put the mean in the middle, 30 grams, and the percentage we're trying to find between 30 and 33, same sort of deal. We're trying to find this area back here for the mouse. So that formula you saw on the previous slide, this Z formula, we're going to do that Z calculation. We'll be using that a lot today. Find the piece of data we're interested in, the boundary of 22. 22 minus the mean divided by the standard deviation of the population, and we find, of course, it's one standard deviation away above the mean, if you like. And the same with the mouse. 33 minus 30 is 3 over its standard deviation of 3, and it is also one standard deviation above the mean. So what is that area? Let's look it up in the tables and see if we can find it. In fact, I hope I've got some tables. Here's a table here for us. So we've got these Z scores here, and we just go down and we find that one standard deviation, a Z score of 1, represents an area of 0.3413. So for both of them, that would be our answer. That area would represent 0.3413 or 34%. This time it says, in fact, it looks like at this point they just don't want us to do the areas. They're just interested in us calculating the Z scores. So what about between 0 and 1.5? What about 2.1 and 0? So we're going to walk through each of these. So let's have a look. Firstly, again, they are putting the mean as 0. They're saying there is 0 deviations from the mean here and a score of 1.5. And again, we would need, let's just see where we go, a Z score of 1.5. Let's have a look at what sort of area that might be. 1.5, 0.4332. Okay, what about a Z score of, between, just get this right, 2.1. So a z-score of 2.1, what sort of area would that represent? So all we've really got to do is look up that z-score for 2.1, go to 2.1, and we find an area of 0.4821. 0.4821 would be that area there. Next one, what about 0.6? What is the area between 0.6 and 1.8? So here we're going to find the area all the way back to 1.8. Look that area up. Look up the area from 0.6 to 0 and subtract the two to find the area. So that's what they're doing here. They find the area for 1.8, find the area for 0.6, and subtract them and find that that middle area is 0.2384. Again, just checking, looking up the areas. 1.8 and 0.6 are the two areas we've got to find. So there's 1.8 at 0.4641 and 0.6 at 0.2257. So we've found the two areas, and now we're going to subtract this smaller area from the larger area to find what's left. That 0.4641 minus 0.2257. 23.84, 24% if you like. And what about a z-score that's below the mean? Z-scores below the mean would have a negative z-score, and a z-score of 2.25 above the mean. What sort of an area is that? Well, this time again, because it's below the mean, we'll have to look up that area, find that area, look up this area 2.25 back to the mean, and add the two together. So the two key areas we're looking for is z-score for 2.25 and minus 0.3. Let's go and have a look at those two. So 2.2, so notice 2.25 is what we're looking for. So we go down to the z-score 2.2, and we've got to go across to 0.5. 2.25 z-score gives me an area of 0.4878. So this is starting to pick up what we were talking about earlier with the ruler in a paper version. You can just place your ruler on 2.2 and read off the graph a little more carefully, or the table a bit more carefully. And 0.4878. The other z-score we had to find was 0.3, which is pretty easy to find. Notice if we had to find 0.34, we'd go 0.34 and we'd find that area. This one, just 0.3, is 0.1179. So we found the two areas, and we need to add them there then, 0.1179 and 0.4878. So that total area there, 0.6057. So I hope you're getting the hang of it as we work through. Well, more of this, we'll put it all together in a moment. Last one, it seems that it wants me to find the area to the right of a z-score of 1.95. So we're going to look up the area for 1.95 and find it, and know that the area to the right up this end must be 0.5 minus that area back to the mean of 0.4744 is going to give me the final answer of 2.56%, or 0.0256. Again, just checking, a z-score of 1.95 should give me that area. Let's go and have a look. Here we go, down the z-score, 1.9. We go across, and there's the 5.4744 is the area under the curve based on a z-score of 1.95. Well, good chance for you to just maybe, we're slogging through some tables there. Believe it or not, we're almost halfway through our slides. So why don't we take this opportunity, take a sip of water, stretch, pause the recording if you need to, and I'll be back with you in a moment after I've done exactly the same, had a sip of water. And there was no other way to do that quietly. So it was one of those bottles that gurgled. But here we go. Let's push on and see what we can discover. So this is the full question, if you like. we're just building on the questions, putting the data together. And we start to read through the question. Remember, I said there's really only so many ways that they can show the question. We've just got to go looking for the key bits of data. Get used to looking for the mean. There it is, the mean of 250 with a standard deviation of 40. And we've got to find the proportion of weeks in which the number of cans returned is somewhere between 170 and 350. And then we'll do B and C. So we'll do each part separately. The first thing I always do is draw a graph. These guys like to put the mean, zero deviations from the mean here. I like to actually write the mean in. I like to put the mean here of 200 and, my mouse is playing up, bear with me. I've got water on my finger. Just bear with me while I try and work out where it is. Get rid of the water off my finger, there we go. So I need 250 right in the middle. And for question A, I would put 170 down the bottom, and I'd put 350 at the top. And then I'd start whacking those in the formulas so that I can find what the z-score is. So the next step is to look for your 350. So let's do the top end first. So 350 is the score I'm trying to find, the top limit, minus 250. How many standard deviations is this away from the mean, with the mean of 250 in the middle, over the standard, divide by the standard deviation of 40, and I get a z-score of 2.5 that I need to look up. Crunch the lower number of 170 minus the mean of 250 over 40. It's a negative z-score, it's below the mean, a z-score of 2. So now I go looking for the area for both of those, and the answers are there, but let's go and just check. Here's my z-score for 2, my area for 2, 0.4772, and my area for 2.5, a bit hard to see there, but it's 0.49, it looks like 0.4938. So because it straddles the mean, we can add the two areas together. It's all of that area, the 0.4772, plus the 0.4938. So 97.1% of our data is between, or 97% of the time, proportion of weeks, we'd be returning somewhere between 170 and 350. Let's do the second one, 260 and 280 for B. Again, draw your graph. I'd put 250 in the middle, the mean, and I'm now trying to find this area between 280. I'd put 280 here and I'd put 260 here. Lets me know that I've really got to find the area of 280, find the area of 260, and now subtract the two to find the grey area in the middle. So do the first one, maybe 260 minus 250 over 40 is a z-score of 0.25. 280 over 250 over 40, 3/4, is a z-score of 0.75, the standard deviation. Let's look up the area for both of those. Maybe have to go back. So it was 0.25, 0.2, go across to the 5. So 0.0987. Just go down to the other one, was oops, I went too far, and 0.75. Let's go and have a look at that. 0.75 as an area of 0.2734. So handy to just write those two pieces of data down, and once we've got those areas, the two areas, 0.2734 minus 0.09887, so minus that 0.0987 will give us the area in the middle. So that's what they've done here, 2734 minus 0.0987, so that area is 17.47% in there. Okay, let's do the last one, C. We've now got to find, well, what proportion would the area be between 200 and 240? Again, mean in the middle of 250, and then we're trying to find 250, 200, and then 240. So I'd put 240 there and 200 here. And really, so we need to find the area for 200 all the way back to the mean, area from 240 back to the mean of 250, find the difference, very similar to what we did last time. We're looking up, put in the 200 in our formula, Z score of minus 1.25, put the area of 240 in, a Z score of minus 2.5. We sort of already did that in the last question. We found that 0.25 was an area of 0.09887. Let's look at the Z score of 1.25. Might be on the next table, yes. A Z score, sorry, 1.2 and across to 5. 0.3944 is my area there. Got the two areas, subtract the two from each other, and we've found the area in the middle, 0.2957. So hopefully, just a bit of repetition there, but by just taking it step by step, you can see the steps. Draw the graph, find your Z-score in the formula, look up the area, and then work out what you're going to do to find the particular area you're looking for. I'll do one more question just to make sure you can skip forward if you've got this. You can fast forward a moment, but I want to make sure that we can work it. If we were in class, I would definitely take the time to make sure we've got it. So sales rep, doing some deliveries. What's the time? Looking for the average time, 20 minutes. Standard deviation of 3. We're going to find the proportion in which it exceeds 21 minutes 48 seconds is less than 16 minutes and exceeds 18 minutes. 3 parts of the question, 3 calcs to do. Let's go for A. Mean, population mean is 20. I write 20 in the middle, and I somewhere write the standard deviation of 3, so I just know where to find it very quickly. And then 21 minutes and 48 seconds, 48 over 60 becomes 0.8 of a minute. So I'm looking for 21.8 minutes, and it says exceeds. So it's more than 21.48. So we're looking for this area here. I'd write 20, then I'd write 21.8, and I'd put shade in this area. This is the area I'm trying to find. Go 21.8 minus 20, divide by 3 is 0.6 is my Z-score, 0.6 of a standard deviation. Look through my 0.6, there it is there, an area of 0.2257. So if that is 0.2257, I'll need to go 0.5 minus that to find that, and that's on the next page. So 0.5 minus the area of 0.2257 gives me the result I'm looking for, 27.43% of the time it would exceed 21.8 minutes. Now we've got to find is less than 16 minutes. Very similar calculation. Mean in the middle of 20. We're trying to find 60. We're trying to find this area here. Put a question mark there. That's what I'm trying to discover. Let's go to the formula. 16 minus the mean of 20 over the standard deviation of 3 gives me a Z-score of 1.33. 1.33. 3.4082 is the area I need to find. Well, that will give me this area, 0.4082. I need this area. So it'll be 0.5 minus the 0.4082 will give me 0.0918, that area there, 9.18% of the time. And what about exceeds 18 minutes? Again, this particular question illustrates the importance of drawing a graph. It just helps you visualize. Again, if you always put the mean in the middle, again, I write 20 there. And by then saying, now what am I trying to find? I write 18 here. I'm trying to find 18, and it says exceeds 18 minutes. So obviously this is less than 18 minutes, anything 18 towards the mean of 20 and above. So anything greater than 18 minutes. Well, that helps me straight away know that my area has to be 50% here. I don't need to look up anything to know that the area all above the mean is 50%. All I've got to do is then add this area here from 18 up to the mean of 20. Key in my formula, 18 minus 20 over 3, 2/3, 0.67. Go looking for 0.67 in my Z tables, normal distribution tables. And 0.6 with your ruler, go across 0.67, 0.2486 is the area. So I need to get 0.2486 for that, plus 0.5, total area. Therefore 75% of the time our results will be greater, our raw score will be greater than 18 minutes. Well, what we can do, this is just a rearrangement of that Z formula to say that if I knew my mean and I know what my Z score is and my standard deviation is, then I can pretty much work out where my scores, what range my scores might be, if you like. So let's have a look at this. We've got some exam results here. Perhaps MBA, Master of Business Administration. The mean is 300. I'd write right in the middle, 300. Standard deviation is 60. And the top 35% are gaining admission into the program. What's the lowest mark that would get us in? So policy, the top 35%. So this area here can be 0.35. We've got to try and find that Z score that relates. But remember, the table doesn't show us the top area. The tables always show us the area back to the mean. So we need to look up an area of 0.5 minus 0.35. We need to find an area of 0.15. So let's go to the table and find that area. So this time, remember, up till now, we've been looking at Z scores and finding an answer of area. Now we know the area and we're trying to find the Z score. So we go looking, and of course, looking at the areas, the further up here, we're getting close to 0.5. We can drop down, we're getting smaller and smaller and smaller. And now we're getting closer to 0.15, 0.15, and of course, I've already highlighted it here. Now, the theory is that if it's exactly equal, you can go, you can actually halve the difference between the two results. Personally, watch what's happening here. We've got 0.3. I'm looking for an area of 0.15, and I see that this is 0.0002, 20, if you like, below 0.15. And this is only 17 above 0.15. So personally, if it was me, I would just go, that's a Z score of 0.39. The author split the difference. Technically, you're only supposed to do it if they're exactly half. Look, it really shouldn't matter too much. I believe you'd get full marks either way. Anyway, 0.385 is what he's suggesting, the average of those two. So he plugs that in. He's looked up the Z score. He's applying this formula here. He's got the Z score in. All he's got to do is plug in the mean, sorry, the standard deviation, and plug in the mean. So it's the mean of 300 plus the standard deviation times the Z score will find me the mark, a mark of 323. So just look at the difference. We knew before the difference, this question, we knew the result. We knew the Z score of 323. We worked backwards with our formula to find the area. This time we knew the area and we worked backwards from the mean with the standard deviation times the Z score to find the result. Building on from that question, it says, what value of marks represent the lower and upper quartiles? And what marks would be the interquartile range of marks? So, topic from a couple of weeks ago showed us that the lower quartile would have 25% of the results below and 75% above. The upper quartile, 25% above and 75% below. And there's the median right in the middle. So if we can really add the mean plus 0.25, the mean minus 0.25 z-score, we will get we'll be able to find um, the results, if you like. I'm just trying to work out the value of marks. Okay, just check with me. Yes, here he is. He's solving it. Okay, so again, we're looking up an area to find a z-score. So let's do that. So we're looking for 0.25. Again, he's saying, yeah, this is getting closer. We're closer. And really, if you look at these two results here, this is 14 below 0.25 and this is 17 above 0.25. I would go with the closest one. I would go with a result of 0.67, a z-score of 0.67. I think he goes with a z-score of 0.675, halfway between the two. Let's see what he does. Yeah, so he's working on 0.675. I reckon 0.67 is going to get us pretty close as well. And so just plugging in the results to the formula, really this will be below the mean. So the z-score times the standard deviation below the mean, and this will be the mean of 300 plus. So if you're working on your calculator, you can see that this calculation is repeated twice. If you wanted to use memory, that's a handy, save you a couple of keystrokes. 0.675 times 60 equals, store in memory, and then you can go my mean plus recall memory gives me the top level of marks, 340, and my mean 300 minus recall memory equals my 259 result down here. Well, what is the interquartile range? The difference between the upper quartile, the middle 50%, if you like, is somewhere between 340 and 259 marks. So there's 81 marks is the range of the middle 50% of students. The central limit theorem, notice the difference in the formula, slightly different formula this time. This is the formula we've been using so far with an item of data minus the population mean over the standard deviation for the mean. And what we're saying now is we could calculate, as long as our sample size is big enough, the central limit theorem suggests that even if it's not a uniform distribution, if it's skewed a little bit to the left or the right, if our sample size is big enough, we can still use this formula to estimate proportions and use the areas under the standard curve. And we're going to get pretty close. And so the formula now is we're taking a range and calculating the sample mean minus the population mean over the population standard deviation, and we're adjusting it by the square root of the sample size, little n sample size. And we're going to use just that formula. So if you see the difference, if you see a question that actually starts talking about a sample mean, doesn't talk about an item of data as all of the last questions did, then you'll know you'll need a sample size. The moment you get that triggers you, hopefully triggers that you need to use this formula, not this one. So watch out for that in questions. Watch out for sample sizes. You use this formula. So let's plug straight into a question. We've got assume the weights of Australian males skewed to the right. So it's not uniform with a mean of 83.6 kilos and a standard deviation of 6. So these are population figures. But if we took a random sample of 25 Australian adult males, what's the probability that the mean of this sample, if you like, the mean weight, would be greater than 85 kilograms? So our sample mean weight. So we're going to use that and work it out from there. So we've got the key pieces of data. We've got the population mean, population standard deviation. Interestingly enough, he thinks a sample size of 25 is enough for the central limit theorem to apply. Other textbooks suggest 30. So he's thinking 25 is all right. Anyway, we'll run with what he suggests. So we're going to we just plug the data straight from the formula you saw on the previous page. This one, we're using that formula there. So we're going to plug in the sample mean of 85 minus the population mean over the population standard deviation divided by square root 25. Pretty easy square root to find, but if it was a little more awkward to find, the order of operations, I would key that in your calculator if you needed to. It's a tough one, you know, like 17.9, you've got to find the square root of that or something. I don't know. You wouldn't have a sample size of 17.9, but never mind. Be that as it may, we would find the square root of that number. I would store it in memory. Then I'd go 6 divided by recall memory equals, store that in memory. Then I know I've pretty much got the denominator covered. I've solved that. And then what I can do is go 85 minus 83.6 equals, divide by recall memory. And I've got my z-score of 1.17. I think it's still a good idea. It's always a good idea to draw your grid so you know what you're looking for. I should have done that first. So draw my little beautiful little normal distribution curve here with the mean of 83.6 right in the middle. And I'm trying to find this area here above 85. So I've found my z-score of 1.17, and I'm going to look that up and find the area here, and then I will know this area here. So we're looking for a z-score of 1.17, 1.17, 0.3790. We now know that's the area there. So 0.5 minus 0.3790 will give me this top area here, 0.1210. About 12% of the time we would expect males sample weights to be, the mean sample weight to be greater than 85 kilograms. A tougher question here because we've got to do a little work with the data a little bit more. So just work with what you know, apply some common sense and see how we go. It says apples grown in an orchard are known to have a mean weight of 150 grams each apple with a standard deviation of 10 grams. It's not a normal distribution, and we've got crates containing 400 apples packed ready for delivery to the markets. Approximately what proportion of these crates will contain apples with a total weight of more than 59.6 kilos? So we're going to do a little bit of calculations before we can really solve it. And what he's suggesting is our sample size of 400 is definitely large enough for us to be able to apply the central limit theorem. So we've just got to sort of convert, if you like, these crate weights to a weight, an average weight per apple, if you like. So that's what he's doing here. He's saying, well, look, if a crate of 400 apples weighs 59.6 kilos, how many grams is that? 59,600. And now he's saying, well, what on average, what's the average weight of apples in that crate? 59,600 divided by the 400 apples is about 149 grams per apple. So that gives us, I'm not sure if I've drawn the diagram for this. Yeah, I did. So that gives us something to work with. With the question we're trying to find, we're going to work out, we've converted the crate weight back to an apple weight. So we can then find, we put the mean in the middle. We've found the mean of our sample to be 149, and let's just go back and check what the question really is asking us. What proportion would have a total weight of more than 59.6 kilos? Well, we've found the weight per apple, so we're going to use that as our criteria and find that proportion. Okay, so we know we're trying to find the area greater. So the area greater than 149. So we know that the area above the mean, this one's below the mean, so really that's 50% plus whatever this area is here. So we need the Z formula to find that bit. So we go 149 minus 150 over the standard deviation over the square root of the sample size. Again, I would find the square root of the sample size, um, then put this bit in memory, 10 divided by the square root of the sample size, half, and then do this bit, recall memory. I mean, this calculation is not too bad, but we're finding a z-score of 2. We then go looking up for that area. Area of 2 is 0.4772. So now we can add the two together. The area above 149, an average of 149 grams, 0.4772 plus 0.5, about 97.72%. Almost there, I believe. A little bit more to go. We're rearranging this Z formula, that same Z formula you've seen, to have a confidence interval, for example. Given that we know what the sample mean, we could estimate within reasonable confidence what we think the range of the population mean is. We could say we're 95% confident based on our sample mean that the population mean is somewhere in this range, the lower limit of this amount and the upper limit of this amount. You'll notice with the formula, again, we've got this repetition. So if I was solving questions here, I'd do this part of the formula, store it in memory, and then I can go, it's the sample mean plus recall memory, it's the sample mean minus recall memory. So we can save ourselves a bit of keystroke, work very carefully, and we've got a better chance of getting the correct result and better marks. Just going to see. So the idea here is, what if we wanted to be 95% confident? What would our graph look like? Well, really, we would want to have 95% of the area under the curve, the whole curve's 100%, leaves 2.5% each end of our graph. That's 2.5% plus 2.5. So there's 5% outside, and there'd be 95% inside the graph. So we're looking at this area here, and of course, half of that 97, if you like, is an area of 0.75. So let's just check that out. We could actually look for the area of 0.475 and work out what our z-score would need to be. Just think it's on here. Yep. So we're looking for an area of 0.475 and trying to find a z-score. And sure enough, it's bang on. 0.475 here is a z-score of 1.96. Either side of the mean covers 95% of the area of the graph. Let's go back so you can see it again. 95% of the graph. So there's my z-score. So what about 90? What if the confidence interval was 90%? Again, we could allow 5% to be this end of the graph, 5%, so 10% outside, would leave 45 into the middle and another 45 below the mean. 45 and 45 would give me 90. So I'm looking for an area of 0.45 to find this z-score. So again, an area of 0.45, this time it's bang in the middle, 0.4495, and there is just 0.0005 below 0.45, and 0.4505 is 0.0005 above 0.45. So this time I can legitimately split the difference between these guys and say the z-score is 1.645. 1.645, right in the middle. And that's where we found the z-score for 90%. Finally, 99%. 99% would leave 0.5% this end, 0.5% this end, and what area would that be? what's half of 49? Sorry, we're looking for an area of 49 and a half. 50% minus that half a percent, 0.495 is the area we're looking for. So what sort of z-score would that be? Here we go, 0.4949 and 0.4951 exactly splits the middle, 0.495, 49.5%. So the z-score is 2.575. So we could be, our z-score to be 99% confident, 2.575. Well, let's see if we can put it all together into a question. And here it says, hey, we've found a normal distribution, standard deviation's 8.5, mean, we're not sure what the mean of the population might be. So we take a sample of 40 adults. 40 is reasonable. That's above 30, so definitely above 25. So we're good to roll with this formula. We find the mean of this particular sample is 125. So pretty much got to plug the data in. Put 125 in there. Put the Z4, we want to be 95% confident. So again, we go back just to check that, where would that 95% confidence interval be? And if you needed to, you'd go back into your tables to just check it that the Z-score is 1.96. Once you know, yes, the Z's 1.96, plug that in your formula as well. So let's see how we do it. We grab the sample mean of 125. In fact, plus or minus, if you like, the z-score of 1.96 multiplied by the standard deviation, pick that up from the question of the population, divide by square root of the sample size of 40. So again, if I was doing this calculation, pretty much I would do root 40 first, store in memory. And it's all multiplied by now, so this is fine. Doesn't really matter what order of operations. 1.96 times 8.5 divide by recall memory equals, store that back in memory, and then I can say it's the sample mean. My population mean upper limit would be sample mean plus recall memory, sample mean minus recall memory, and I would have those two results. I'd say I could be 95% confident that the population mean would be somewhere between 122.37 and 127.63. Last slide is this. You are expected, you have the tools, you have the skills at this point to solve pretty much every tutorial question. We'll be working through this in class on Monday and Thursday. But so look at the video, make sure you're comfortable with how these calculations, that will make it flow more easily for you, obviously, when you get to class. But I will suggest you can check your answers. If you wanted to chase up there's two links. Is quite a smart guy, David Lane, sort of designed these calculators that help you they just draw a nice little graph. You can plug in the mean, the standard deviation, and what you're trying to find, and press the calculation button. Remember, you need to be able to, be confident to solve it on your own, but maybe you might want to just use his little calculators to check your work, see if you're on the right track. Check your clerical accuracy. I guess that the hint with all of these questions is take it nice and slow, find the right formula, plug the data in, and you'll get full marks. So I'll leave it at that. Look forward to catching up with you in class.